Good morning, class. We are looking at Chapter 5, Section 5.4, the substitution rule. So we are looking at various integration formulas for anti-differentiation and the fundamental theorem of calculus, reminding you the derivative of the integration gives you the function back, and the integral of a to b f of x dx is a definite integral is a number capital F of b minus f of a, where capital F prime is lowercase f of x. And here's the substitution rule that we are going to discuss in a moment. So what is the substitution rule? That's what we want to discuss. 5.4, the substitution rule. Integration by substitution is the reverse process of the chain rule in differentiation. We know how to differentiate this. So capital F prime of g of x, if we want to differentiate it, capital F prime of g of x times g prime of x. In other words, d dx of this expression is capital F prime of g of x, g prime of x. Normally, capital F prime is the same as lowercase f, so f of g of x, g prime of x. So if we integrate this side with dx next to it, it must give us this plus a constant. That's the idea. So let u be g of x, then du dx is g prime of x, therefore du is g prime of x dx. The integral of f of u du is capital F of u plus a constant, where u is the same as g of x. So here's the theorem. Over any interval for which u equals g of x is continuously differentiable and f is continuous on the range of this function, the following relationship holds. The integral of f of g of x, g prime of x dx, where g of x is the u function, g prime times d, their product is du. We are looking at the integral of f of u du, which is capital F of u plus c, and u is g of x is capital F of g of x plus c. So it makes it the reverse process of the chain rule, everybody. Let's look at a simple example. The integral of 2x times x squared plus 5 quantity cubed dx. This is 3, so you could always raise it to the power of 3, but what if it were 30? Then it would make it difficult to integrate this. If you have a couple of polynomials, in this case x squared plus 5 and 2x, the more complicated one, in this case x squared plus 5, is a choice of you. Notice if you differentiate this, du dx is 2x, which makes du 2x dx. Now we move things around. I'm going to move the 2x next to dx because I want to make sure it's clear to everybody. This is u and this is du. That's the reason. If you don't do it, it's okay, but it's really a good practice to do it. So you're looking at the integral of u cubed du, which is going to use the power rule, resulting in 1/4 u to the power of 4 and a constant. And finally, you replace the u, and you get 1/4 x squared plus 5 to the power of 4 plus c. So what is the technique? What is the tip? Look for a function u equals g of x anywhere in the integrand and its derivative du or g prime of x multiplied by dx. So look for a function that can represent the u and then its derivative times dx. And anytime you do the substitution, that is your very first step. You have to write down the choice of u, and then you calculate du. That's the very first step before we move on. Again, we are dealing with polynomials. The one which is more complicated, in this case, x cubed plus 1 should be the choice of you. And notice that 3x squared is the derivative of that. Note that 3x squared is the derivative of x cubed plus 1. So we are going to move the 3x squared next to dx. And if we choose this one to be u, this one is derivative, and times dx is du. So we are looking at the integral of u to the power of 10 du, a simple case of a power rule. So 1 over 11, u to the power of 11, and a constant. Reversing the substitution, meaning replace the u with x cubed plus 1, and that's the final answer. In this example, the integral of 9 parentheses x squared plus 3x plus 5 close parentheses times 2x plus 3 dx. Again, clearly, this is the more complicated polynomial. So that's the choice of u. U is x squared plus 3x plus 5. Clearly, the derivative is 2x plus 3. This one. Therefore, du is 2x plus 3 times dx. You don't have to move anything around. You are looking at u here, du here. Whether you keep the 9 inside or outside the integral sign makes no difference. It's a multiplier, it's a coefficient, it remains. And this is basically the one that you're integrating, u. So you get 9 halves u squared plus c, because this gives you half of u squared plus a constant. Reversing the substitution means replace the u with x squared plus 3x plus 5. That's the final answer. And as always, you can check by differentiating. If you differentiate this, it gives you the same thing without the dx. So the final answer is 9 halves x squared plus 3x plus 5 quantity squared plus a constant. I have a couple of questions that I want to make sure you see it side by side so we can compare and contrast. Both of them are fractional formats. Both of them are fractions. This one is a polynomial, this is not. But the concept is the same. Number one, you are going to simplify if you can. This one you can't. So the denominator is a choice of you. As you can see, the derivative of the bottom is the top. Therefore, du is e to the power of t dt. We move the dt up so it becomes clear that we are looking at du over u. And therefore, we are dealing with natural law. So ln of absolute value of u plus a constant, replace the u, and you're done. If you lose the absolute value, it's fine because this expression is positive 5 plus e to the power. Now, what happens in part B is that you want to simplify if you can, and you cannot. I'm going to remind you of the reason, and that is when you have the expression ax squared plus bx plus c, as it is the case here, and therefore a is 1, b is 2, c is negative 1, you calculate b squared minus 4ac. If this expression is a perfect square, it can be factored. Otherwise, it can't. And this is 8. 4 plus 4 is 8. It's not a perfect square. Cannot be factored. So u is the denominator. Notice if you differentiate du dx is 2x plus 2. Or 2 times x plus 1. Therefore, du is 2 times x plus 1 dx. Now, I'm going to put the dx in the numerator so it becomes clear that the top is almost du. So what happens when a number is missing? You have two choices. In your text and in most texts, they solve for dx. I'm going to give you an easier way. If a number is missing, you can put it in there and undo it with its reciprocal. It's important that the product must remain as 1. In other words, you're not changing anything. So if it's 2, it's 1/2. If it's negative 2, it's negative 1/2. So the reciprocal, the product must be positive 1. And so now you're looking at du over u, and the 1/2 remains outside or inside the integral sign, makes no difference. This is a natural log. And you replace the u, and you must keep the absolute value because this expression can be positive or negative. Whereas this one, you can lose it. So half of natural log of absolute value of x squared plus 2x minus 1. That's the constant. Now, what happens, and again, on the same page, I want you to see that. What happens if we have reciprocal of one of those? For example, the reciprocal of part A, or even for that matter, part B, you don't have to do substitution. Okay. If you make up two fractions, this is one of them. 5e to the power minus t, and this is one of them, 1. Then no need for substitution. As you know, this one is the same thing. You divide by -1 becomes minus 5e to the power minus t. This is t and a constant, and you're done. Same thing if this was over that, you have to do long division or synthetic division and then integrate it. So that's why I thought it was important to see them side by side, compare and contrast two fractional formats versus the format that doesn't require the substitution method. What happens when e to some power is involved? In those cases, the exponent of e is a choice of u. Now, if u is x to the power of 5, its derivative is 5x to the power of 4. Therefore, du is 5x to the power of 4 dx. So we are looking at this format. I'm going to move this next to dx because I want it to be clear that we do have e to the power of u du. And this, everybody knows the answer is itself, e to the power of u and a constant. And replace the u, reverse processing, gives us e to the power of x to the power of 5 plus c. And as always, if you differentiate, the result must give you this one without the dx. So if the e is involved, the exponent is a choice of u. Same thing here. The exponent is x to the power of 5 minus 2 is the choice of u. What is the derivative? 5x to the power of. What is du? 5x to the power of 4 dx. And so let's move x to the power 4 next to dx to see what we are dealing with. Everything is in order. We have e to the power of u, but we don't have du. Why? Because number 5 is missing. Again, in most texts, they solve for dx. I'm not going to do that. It is easier to notice 5 is missing, which is a number. So if I put 5 here, what do I need that? Outside, it's reciprocal 1/5. By the way, you might say, okay, I'm going to put the 1/5 inside the integral sign. Makes no difference. It's a multiplier. It will remain as a multiplier coefficient. So you have 1/5 the integral of e to the power of u du. And so the answer is itself. You keep the 1/5. And now when you replace the u, it's 1/5 e to the power of x to the power of 5 minus 2. And a constant, as always. Differentiation will result in the same thing without the dx. So very straightforward, everybody. So notice I didn't solve for dx. I'm going to look at an example that I'm going to do that, and you see really makes no difference. The more complicated the case, the easier the method that I showed you, just throw in a number and undo it. For example, right here, 3x plus 7 is a choice of u. If I differentiate du dx is 3, therefore du is 3 dx. Now, the way I do that, I basically notice that this one, 3 is missing. I throw in 3 and 1/3. The way they do it, by them, I mean the most text. They solve for dx. So let's solve for dx. That means du over 3. Again, this is simple enough, it really makes no difference. The more complicated the case, the faster and easier the method I've shown. So this becomes that. So that gives rise to this 1/3. And by the way, square root of u is u to the power of 1/2. What do I do? Well, I look at this one. And I look at this one and I say, oh, okay, number 3 is missing. I'm going to throw in number 3. How do I undo it? 1/3. It's reciprocal. And that's exactly what we have here. Of course, you're not going to write square root of u and so on. So it's the same thing. Which one is easier in this case? I don't think it makes much of a difference, but in many cases, I think this method is easier. In any event, this one uses the power rule, 1 over 1/2 plus 1 u to the power 1/2 plus 1. Keep the 1/3 and a constant. 1/2 and 1 is 3/2. So this is 3/2, everybody. And this is 2/3. And this is 2 over 9. So 1/3 times 2/3 gives you 2 over 9 u to the power of 3/2 and a constant. What is u? 3x plus 7. If you want to put it back in the same format with the square root, you can do that. Becomes 2 over 9 square root of 3x plus 7 cubed and a constant. You can do that. This case doesn't make much of a difference. In some cases, it might. Again, why do I have the two questions side by side? Both of them involve ln x. At this level, anytime you see ln x, that is the choice of you. Its derivative is 1 over x, therefore du is 1 over x dx. Now, I write it two ways. I write it in this fashion, 1 over x dx, also as dx over x, to make a point. They're the same. So if you see any of them, it's fine. So I like to make changes so that it becomes clear what components I have. One of them is ln x to the second power. One of them is 1 over x dx. Therefore, this is clearly u squared. This is clearly du. Again, the reason I go from here to here, just to make sure everybody can see this transition through the u substitution. I highly recommend you do that to make sure you know exactly what you're doing. It's a simple case of a power rule, makes it 1/3 u cubed plus a constant. Replace the u, and you're done. Before we move on, so the answer is 1/3 ln x to the third plus c. I want to make sure we don't confuse the following, everybody. Ln x to the third means ln x times in itself 3 times. It's not equal to this one. I've seen students making that mistake. This is the same as 3 ln x. Please don't mix them up. So, part B. We are going to rewrite part B as components so it becomes clear what we are dealing with. So I'm going to rewrite this as 1 over x, 1 over ln x times dx over x. Now, on purpose, I'm not going to write 1 over x dx. I'm going to write dx over x to just mention these two are the same, everybody. 1 over x dx or dx over x makes no difference whatsoever. So what we are dealing with, 1 over u du. And it's a simple case of a natural log. So natural log of absolute value of u plus a constant. The u itself is ln x. So it's ln of absolute value of ln x plus c. As always, if you differentiate, you get this one without the dx. That means you get 1 over x ln x dx. That's what you get. All right. Let's look at this case. And again, there's a reason that I have a couple of questions side by side. When sinusoidal functions, that means sine and cosine, are involved, how do you deal with them? If the argument of the sine or cosine has an exponent, in this case, x has the exponent, then that is the choice of u, including the exponent. The choice of u is x squared. The derivative is 2x. Therefore, du is 2x dx. I'm going to move the x next to dx. So it becomes apparent that what is missing, what is given. So this is obviously sine of u, but this is not du. The reason it's not du because number 2 is missing. Because we are dealing with a number, we can throw in the 2, and it's reciprocal 1/2. Their product must always be only one, positive one. So you're dealing with 1/2, the integral of sine u du. And that, the derivative of sine is cosine, but the integral is negative. So negative 1/2 cosine u plus a constant. Okay, talking about this one. And u reverse processing gives us x squared. So negative 1/2 cosine x squared plus a constant. You can always differentiate this and you get this one without the dx. So in this case, the argument has an exponent, and that's the choice of u. What happens when we have both sine as well as cosine? Then what is the process? When you have both of them, the one that has the exponent is a choice of u when you have sine as well as cosine. But the one that you choose it without the exponent. So sine has the exponent. Sine is the choice of u. U is sine x. The derivative is cosine, so du is cosine x dx. So the integral of u squared du, simple case of a power rule. One-third u cubed and a constant. Replace the u. One-third sine cubed x plus c, or one-third of sine x to the third power. It means the same thing. And as always, if you differentiate this, must give you this one without the dx. So sine and cosine, both of them are involved. The one that has the exponent is a choice of u without the exponent. So what about this one? Cosine has the exponent. The integral of cosine to the power of 20x sine x dx. So u is cosine x. Its derivative, it's negative sine x. Therefore, du is negative sine x dx. So when we look at this one, sine x dx is there, but not a negative sign. So big deal. Put a negative in and out. So if I put a negative sign inside, to undo it, I put a negative sign outside. Their product must be 1, and it is. So we are in good shape. So what we are looking at is the minus integral of cosine to the power of 20x times minus sine x dx. So that makes it u to the power of 20 du. So simple case of a power rule. Negative remains. 1 over 21 u to the power of 21 plus a constant. And u is replaced with cosine. We get negative 1 over 21 cosine of 20, cosine to the power of 21x plus a constant. If you differentiate, you get this one without the dx. So I think to recap, we looked at the case where the argument had an exponent, and that was the choice of u. We look at the case that sine had the exponent, sine was the choice of u. And the case that cosine had the exponent, cosine was the choice of u. Substitution for definite integrals. The integral of a equals 1, 2, b equals 2, 2x times x squared minus 1 cubed dx. When it comes to definite integral, the answer is a number. So there are two methods. One is to keep the original limits and go back to the original limits, return to the original variable. Now, clearly, we need the substitution method. The more complicated piece is x squared minus 1 is a choice of u. The derivative is 2x, therefore du is 2x dx. To see what's happening, we're going to put the 2x next to dx. So simply put, we have u cubed times du. However, the limits of 1 to 2 pertain to the variable x, not necessarily to the variable u, and therefore I'm going to write without the limits. In fact, I put a question mark, meaning we don't know what the new limits are. For now, we're not going to care. So the first method is not to find the new limits. A simple case of a power rule, 1/4 u to the power of 4. Again, what are the limits? I don't know. We want to keep the original variable. We are going to change the u to x squared minus 1. Therefore, the answer is 1/4 x squared minus 1 to the power of 4. But now we can use the original limits 1 and 2 because they pertain to the variable x. If I put 2 here, I get 4. Minus 1, 3 to the power of 4 is 81. If I put 1, I get 0. So 1/4, 81 minus 0 is 81/4. I'm done. So I went back to the original variable, original limits. Everything works out. And normally there is not a huge difference. However, the second method is to keep track of the change of variables in the limits of integration, meaning the lower limit is 1, put it into the u. So the lower limit x equals a equals 1. We say a in general because it doesn't have to be 1. Whatever the lower limit is. And this is g of x. So let's evaluate g of a, namely g of 1. If I plug in 1, I get 0. For the upper limit b equals 2, x should be the upper limit. It happened to be 2. We call it b in general. So now we're going to evaluate g of b, which is g of 2. 2 squared is 4 minus 1 equals 3. And so over here, everybody, so over here, now we can say from 0 to 3. So we get here 0 to 3. So this is the same as this, is the same as this. Now, clearly, if I put 3 here, 3 to the power of 4 makes it 81. 0 gives you 0, so 81/4. Now, which one is easier? Most of the time, this ends up being easier, but ultimately, it's your choice. Now, so what? Here's the theory. If g prime of x is a continuous function on the closed interval of a to b, and f is continuous on the range of u equals g of x, then the integral of a to b f of g of x, g prime of x dx, is the integral of f of u du from g of a to g of b. So what it means is that just plug in the limits into the u substitution to find the new limits. That's all it means. That's the meaning of this theorem. So here's an example, the integral of 3 to 4x squared of 25 minus x squared dx. That is going to use the substitution, and we know the answer is in numbers. So 25 minus x squared is the more complicated polynomial. That is the choice of u. The derivative is negative 2x. That means du dx. Therefore, du is negative 2x dx. So let's rewrite this by moving the x next to dx. We see that everything is in order. We have square root of u here, but we don't have du. What is wrong? Nothing. Negative 2 is missing. You can solve for dx or say, okay, negative 2 is a number. So plug in negative 2. If you plug in -2, you have to have its reciprocal -1/2 as well, because their product must be positive. And now you're looking at -1/2, the integral of square root of u du, but I'm not going to write the limits 3 and 4 because they no longer pertain to u. Therefore, we have to find the new limits. Let's finish this with just the way it is, and ultimately we figure out the new limits. So this is u to the power of 1/2, and we write it in this fashion so we can use the power rule. We have done this before. This doesn't change. Remember, this becomes 1/1/2 plus 1 u to the power of 1/2 plus 1. And as you recall, this is 3/2. This is the reciprocal of that 2/3. Multiply by -1/2, you get -1/3. And now I can go back to the original variable and original limit. So I'm going to change the u to 25 minus x squared, and I can use 3 to 4. And you can do the math, and you're done. However, I like to find the new limits as well. And this is an example that using the new limits actually is easier. So how do we use the new limits? First and foremost, let's plug in this one here. When you square 3, you get 9. 25 minus 9 is 16. So that's the lower limit. The upper limit, if I put here, 4 squared is 16. 25 minus 16 is 9. That is the upper limit, everybody. And so you plug it. To make it easy, we are going to keep this out. So minus 1/3 times 9 to the power of 3/2 minus 16 to the power of 3/2. Those are easy calculations. Let's do the basic math. Square root of 9, 3 cubed 27 minus 16 to the power of 3/2. Square root of 16 or 4 cubed is 64. 27 minus 64 is minus 37. The product of these two numbers is positive 37. So it's fairly basic, but I hope you see that the new limits makes it a tad easier to evaluate versus the original limits. Okay. We want to evaluate the integral, and this is a definite integral. It's going to give us a number. And so we need a u substitution, and we are dealing with polynomials. This is the more complicated polynomial. That's a choice of you. If you take the derivative, it becomes 6x squared. So du is 6x squared dx. To understand what we are dealing with, I'm going to move things around in the following manner. I put the x squared next to the x. And so I have u cubed, but I do not have du because number 6 is missing. Again, I'm not going to solve for dx. Instead, I'm going to say, okay, number 6 is missing. So I'm going to put it here. But it's reciprocal, 1/6. So I'm going to put both of them. Okay? Because their product must be 1. So now you're looking at 1/6. The integral of 0 to 2 is no longer there. U cubed du, because what are the new limits? We'll figure it out. So again, on purpose, I put the question mark because we're going to figure out the new limits, everybody. So, what are the new limits? If I put the 0 in here, I get just 0 minus 8. If I put 2 here, 2 cubed is 8. 2 times 8 is 16. Minus 8 is 8. So it's going to go from negative 8 to 8. Okay? And 1/6 remains. U cubed gives us 1/4 u to the power of 4. We're going to put these two together and make it 1/24, and we're going to keep it outside. That's what we are going to evaluate. Or replace the u with 2x cubed minus 8. And now evaluate it from 0 to 2. And I hope you see that it is easier to use this one, and I'll tell you why in a moment. Over here, we get 1/24, 8 to the power of 4 minus negative 8 to the power of 4. Now, because the exponent is even, this is the same as 8 to the power of 4. Please understand, if it was odd, that wouldn't be the case. They cancel each other. We end up with 0. And that's what makes it easy to understand, okay? If you go with the other one, in other words, if you go with this one, it's going to take a tad longer. This is much easier to see the answer is 0. Very simple, everybody. Example 10 from example number 34. The rate of growth of a fish population was modeled by the equation g of t equals 30,000 e to the power of negative 0.60 over 1 plus 5 e to the power of negative 0.60 quantity squared, where t is measured in years since 2000 and lowercase g of t in kilograms per year. So whenever we discuss the rate in calculus, we are talking about the derivative function. If the biomass was 40,000 kilograms in the year 2000, what is the predicted biomass for the year 2020, and round it to the whole number. So it's really important to understand we are talking about the derivative function, okay? So if capital G of t represents the biomass, okay, then the growth rate, its derivative, capital G prime of t is lowercase g of t. And because we are dealing with the year 2000 with this much, and then what happens in 2020, this will be our initial value. G of 0 is 40,000, meaning the year 2000 corresponds to 0. So for example, the year 2005, then it's 5 years later, t is 5. 2010, t is 10, 2020, t is 20, and so forth. And so based on the accumulated change, the net change theorem, and we have seen this type of question, the amount of increase is the integral of that from 0 to 20. The reason it's from 0 to 20, this is the initial year, and then this is 20 years later. So the difference between 2020 and 2000 is the number we're going to put here. So let's plug it in. The only reason we have this question here, because in this part, it uses the substitution. So we have the denominator being squared. And remember, when we have a fractional format, first we try to simplify. If not, the denominator is the choice of u, of course, without the exponent. And so notice that if you differentiate this, you get the same thing, 5 e to the power minus 0.60 times minus 0.6. The product of these two numbers is negative 3 e to the power of negative 0.60. So that's du dt. So what is du? Minus 3 e to the power minus 0.60 dt. Now, everything is in order. We want negative 3. We don't have it, but we have 30,000. You have two choices. You can take the 30,000 out, then throw in negative 3 and divide by it. Or say, you know what? 30,000 is actually a good number because the product of negative 3 and negative 10,000, you're going to keep this one out. So you have your negative 3, and you're going to bring the dt up because now you recognize this number remains. This entire thing, we kept the negative 3 and we put the dt up. This is du. And I'm not going to write the limits yet. This uses the power rule because we're going to write it as u to the power of negative 2. Remember, this one is so 1 over negative 2 plus 1, u to the power of negative 2 plus 1, which makes it negative u to the power of negative 1. Negative u to the power of negative 1. This thing is the same as this thing, which is negative times negative, positive 10,000 over u. Positive 10,000 over u. Now, what are the new limits? Well, let's find out. First, we're going to put 0 in here. So if I put 0 in here, I get 1 plus 5 e to the power of 0, which is 1, gives me 6. The lower limit is 6. What if we put 20 in here? We get 1 plus 5 e to the power of the product of negative 0.6 and 20, which is negative 12. So the lower limit is 6. The upper limit is 1 plus 5 e to the power minus 2. And this one, we put it as 10,000 over u. For the sake of calculation, we're going to take the 10,000 out, and we're going to say 1 over u from 6 to this number. This number is close to 1 because e to the power minus 12 makes this very small. I'm going to write it as 1 point with many zeros, 1.00004 zeros and 31, just to make a point. Yes, you can get a number which is not 1, but it's almost 1. So if you treat that as 1, 10,000 times 1 over 1 minus 1 over 6, you put it into a calculator. They are asking for a whole number. Next to 3 is 3, so it doesn't change. 8,333 kilograms. Initially, in the year 2000, we had 40,000 kilograms. They add up, and the expectation is to have it in the year 2020. The sum of the two, 48,333 kilograms of fish. That's their biomass. Now, if you recall, even when we didn't need the substitution method, I showed you the second method. The second method being going back here, the G is this one and a constant. Remember that? Because we worked it out, we have this 10,000 over U and a constant. So what is U? This one, plug it in. So that gives you a general solution. What is the initial value? So G of t is 10,000 over 1 plus 5 e to the power minus 0.60 and a constant, and G of 0 is 40,000. that will help us find the constant. This is a general solution. We are going to go to a particular solution as a result. So let's plug in 0. If I plug in 0, I get 10,000 over 1 plus, remember this becomes e to the power of 0 or 1, so 1 plus 5, and a constant, and it's supposed to be 40,000. So I'm going to divide 10,000 by 6, subtract it from 40,000 to get C, which is 38,333. And I'm going to say G of T in general in this, in particular, is this plus this number. And I want, for the year 2020, I want G of 20. If I plug in 20 here, I get the same number here. The advantage is, if the question has several parts, what is the biomass for the year 2025? You replace this one with 25 right here, 25. 2030, you replace it with 30, so on and so forth. That's the advantage of that. Again, I have a couple of questions side by side because I want you to see and compare and be able to distinguish between the two. In both cases, the denominator 1 plus x squared, not to the power, is the choice option. The derivative is 2x, therefore du is 2x dx. So this is clearly just given as du over u, and the integral of du over u follows the natural log. So it's ln, okay, natural log of absolute value of u plus a constant. So you put that, it's that simple. And you replace it with 1 plus x squared. And the reason I changed the absolute value to a parenthesis, just to emphasize, 1 plus x squared is positive, everybody. You could do that. If it's not, you can't, okay? And we're done. And as always, you can differentiate this and it gives you this one without the dx. For part B, we use the same substitution. For part B, we use the same substitution. However, we bring the u up, becomes u to the power of -2 du, and therefore we are going to use the power rule. So that's the difference. This will end up using the natural log, but not this one. And that's the idea. Now, we've done this before. 1 over, in fact, in the previous page, 1 over -2 plus 1. U to the power of -2 plus 1 and a constant. And just this part, this becomes negative, right? Becomes -1. So this whole thing is just a negative sign. So minus u to the power of -1, which is minus 1 over u. And the u is replaced with 1 plus x squared. So we get minus 1 over 1 plus x squared and a constant. So similar questions, different results, because this exponent, this denominator has no exponent, ends up being a natural log. This one has an exponent. Any exponent, it ends up using any exponent. It ends up using the power rule. And that's the idea, everybody. Now, this one I chose because it may not be clear that you have to use a substitution, although ultimately it becomes easy and you can see that. But the way the substitution work, again, you have a fractional format. You really have 1 over x plus 3 times dx. Let me also write that, so because in case you come across that format, this is, everybody, the same as 1 over x plus 3 times dx. So u is x plus 3, the derivative is 1, and therefore du is dx. And I wrote it in that format so you can recognize it either way, okay? So it looks like the integral of du over u, which is just the same as this one, becomes a natural law and a constant. And now u is replaced with x plus 3. And you replace it, and you get ln of x plus 3. And that, you have to keep it in an absolute value, because this expression can be positive or negative, whereas this expression, it's always positive.